the first lecture of the Quantitative Trading Program led by Imperial Blockchain Group. My name is Ahmad Danesh and I will be giving you an introduction to Python. The course structure is fairly straightforward. I will be giving you an introduction to the Python programming language, and subsequently in the next session, Imran Khan, the blockchain president, will be giving an introduction to pandas. This will be followed by a session on an exchange API and covering the basics of crypto instrument fundamentals. Following that, there will be an introduction to DeFi and MEV strategies led by GSR, and a session on risk management for our fifth session. And following that, we will have one session on-chain options led by Open, and a bonus lecture given to us by Nomura on some macroeconomics. So, we're all here today to learn about why programming in Python would be beneficial in order to help us navigate the world of crypto. But I first wanted to discuss how programming in itself might be beneficial in general. Why would you want to learn how to program in the first place? Well, essentially, computers are very advanced machines, and they can do tasks that humans can't do on a repetitive level. If we want to, for example, loop numbers from the start to an endpoint, computers can do that much faster and generally much more accurately than humans can. As I said, computers can generally give much better accuracy than humans, although this doesn't exist all the time. There are certain stipulations which would suggest that the human intervention might be better than computers, but most of the time, computers are inherently much more better at higher accuracy processes than humans can tend to be. As a result, they are very helpful for solving complex problems that we might have. For example, if you study maths, there might be certain algorithms that you might use a computer to be able to evaluate. Also in physics, if you're studying certain for example, experiments, you might be using a computer simulation. This extends to all our different parts of our lives, and computers have inherently helped us to solve various different problems. As we may already know, in the 21st century, we are able to use the internet to be able to discover information. Computers are also very useful, as they can also be connected to the internet, and they can also scan information on the internet in order to make use of what's available. We might be using that, for example, to connect to an API or to an exchange in order to get the best price information for a certain crypto coin, or, for example, for specific needs that we might have. As a result, given that computers are much faster than humans can generally be, that might help us quite a lot when we're doing quantitative trading. It helps us to execute orders far quicker than an individual person might on the sales and trading floor at an investment bank, for example, or in any proprietary trading firm that you may be able to find, especially in the crypto world. And of course, we wouldn't actually be doing programming if it wasn't fun in the first place. Programming is actually a very fun exercise, and it helps you develop your problem-solving skills. But that only happens if you're being taught correctly, or if you've got a good instructor that will be able to help you understand things at an independent level. And that is, of course, the aim of today's session. Before we actually write any code that you might have done in the past, it's a good actually to check, how does a computer actually work? Of course, having an understanding of how the computer might be doing its processes, or how it thinks when it does execute certain processes, will help us to optimize our program. And when I mean about optimizing, I mean that we might be able to do it a lot faster and a lot more efficiently. So let's have a look at some of these points. I mean, like humans ourselves, we obviously have a certain language in which we communicate, and obviously both of humans in any part of the world, assuming they're speaking the same language, have all learnt it the same way, so they're able to converse with one another appropriately. Machines are very similar. Machines are able to think in a language that we tend to call machine code. Well, we call it, obviously it's machines, so that's why we call it machine, but they use something else. They use coding in order to be able to perform their processes. On a simplistic level, machine code is essentially the instructions that we feed a computer and we ask it to execute. So if we give it the right instructions and the right data to work with, it will be able to execute it without error. It will be able to do the instructions that we want it to do without error. It's a bit like handling a recipe. If you're trying to cook, for example, a cake. When you understand the instructions and you're given the right information, you can make a perfect cake. But obviously, if you give it the wrong instructions or you don't give the right ingredients, you tend to produce a very bad cake. Here's one example that you may not be familiar with, but you may have come across the concept. So when we first study programming, you'll be learning how to write a message to the screen titled "Hello World." And the computer actually doesn't actually take our line of code and execute it directly. It actually translates translates our code to a code that it can understand better, to a language that it can understand better. And on the screen here, you can see the 32-byte Linux system's machine code just to be able to print "Hello World." And of course, as you can see, there are lots and lots of lines that we would have to write just to be able to print this one message. And this might not just be the instruction, print "Hello World," it might also have to be certain memory allocation or getting it to be able to store information in the right place. And as humans, we haven't got the time or the patience to be able to code all these lines one by one. We'd like to have a much higher level language that will help code the language, help code our program in a way that we can be able to read it, but for the computer to be able to execute when it translates it to its own machine code. So, when we're actually looking at the computer, we have the machine code that the computer uses to execute the program. And essentially, the computer's main brain, or the sort of thinking space, is called the central processing unit, CPU. And that's obviously quite indicative by its name. It processes all the instructions at a central part of the computer. Many of us may have some CPUs available to us. There are CPUs that are made by AMD, and most of us, or maybe the Apple M1 that's been recently released. And recently, for many years, there was the Intel series, the i7 series, and it's a very simple chip. It's quite actually small when you hold it in your hand, but it's actually got the processing power for the computer to be handling thousands, if not millions, of instructions every second. And I'm not going to bore you with the maths, but it's very, very, very impressive how they managed to pack all this technology into a very small cell. The problem is, as I alluded to earlier, is that machine code isn't exactly something that we can read easily. Of course, we want to print out the message "Hello World," but writing all that code just to be able to do one simple job is going to be counterproductive, as we're wasting a lot of our time. So, the main aspect of programming that was first alluded to in the 60s and the 50s was how could ordinary people like ourselves write code for computers very quickly and very simply. And over the course of many decades, there was the idea of developing higher level programming languages. And you'll see in a minute what I'm alluding to when I'm speaking about a higher level. It's essentially a level that's much more closer to the ability for humans to be able to read the instructions than it is for the computer to be able to read the instructions themselves. And one of the languages that we're going to be using is the world famous Python programming language. I'm going to talk a bit about that briefly. So, Python was actually developed by Guido van Rossum, who actually was doing it as a part-time hobby in order to create a language that could be read very simply by humans like ourselves. Essentially, the scheme of the programming language is that we have a high-level code that we can read as human beings. And what I mean by high level, as you'll see momentarily, is that it's very far away from the machine code when you look at it in terms of the number of layers in the hierarchy. In order for the computer to be able to execute the instructions, computers need machine code. So what happens is there's a set of processes that take place inside the computer to be able to translate human-readable code into computer-readable code in terms of the machine code. Firstly, the code is compiled, and at a very, very high level, this basically means that we are checking if the program is error-free. Please do know that that is a gross oversimplification, and the compiler is much more powerful than just checking whether the program is actually free. It actually tries to run the program and tries to put it together. That's what we mean by compile, because the verb to compile means to put something together. Once a program has been successfully compiled and it doesn't have any errors, it's then translated a bit further into an intermediary language called bytecode, which is closer to the machine code that the computer wants. This is then taken care of by the Python virtual machine, which is a separate program that helps to translate the bytecode into machine code for the CPU to be able to read. And this is when we eventually reach the machine code at the far bottom. And as you can see, there are 5 layers starting from machine code to the high-level code. And that's what we mean by the hierarchy with respect to referring to our Python code as high level, because it's so many levels higher than the machine code right at the bottom. And then that machine code is, of course, fed to the CPU, or as we refer to, the central processing unit, which then executes the instructions and helps deliver the desired result that we want. In fact, what happens in Python is the scheme is abstracted a bit further. The compiler, the bytecode, the PVM, and the machine code is actually all put together into one unit that we call the interpreter. And the interpreter, at a very high level, essentially takes the high-level code and runs all the processes to interpret it to a language that the CPU can actually read. And it's a bit like if you're speaking from English to Spanish, that you have to have someone interpreting it in the middle to be able to relay your message to someone that might speak Spanish, for example. So we've all got a computer in front of us. I assume that's how we're going to be how you are watching these lectures. So to be able to program our computer, we're going to need a couple of tools in order to get going. First, we're going to need an editor. Many of you are familiar with the example of Google Docs or Microsoft Word to be able to write something onto the screen, write something into so that the computer can save it or use it to run it, or maybe print it, for example, if you're using Google Docs. And that is the function of the editor. Simply chuck something on the screen that shows you what you're writing. It's a bit more developed, but we can actually have more than just the editor. We can have something that's called an integrated development environment. These are obviously three words that we refer to as the IDE, so it's best to actually look at these on a separate level. The environment essentially is the place where you actually develop your code. It includes the editor, but it has many more things. For example, the compiler or the file explorer, where you look for your files that you've written separately in other areas of your computer. And what we do in the IDE, and what the IDE does when we look at it, when we use it, is it brings the editor, the compiler, the file explorer all together in one window. That's what we mean by integrated. So we have an integrated environment where we can develop our code, i.e. integrated development environment. Very simple. You're going to be finding yourself using something called the shell. And the shell essentially is what we refer to as an interface, something that you can interact with. It helps you to communicate with the heart of the operating system that you're using. And the operating system is essentially just the software, just the overarching software that helps you to run certain programs. For example, I'm here using a Mac OS system that helps me to run something like Virtual Studio Code or PowerPoint or Microsoft Word or Google Chrome. Whether you might also be able to use other operating systems such as Windows, which is also very, very useful. But also there are some operating systems that are free or open source, such as Linux. We'll be speaking about the shell a bit later when we're actually delving into the code itself when we're using our editor. And I've already mentioned a bit about the editor that we're going to use. And we're going to suggest that if you're asking the question, what editor should I install on my computer, or in fact, what should I install on my computer in terms of the software, we're not actually asking you to install much at all, because computers have evolved to take care of many of your prerequisite needs. The one thing that we would recommend is a very good IDE that includes an editor. And we would recommend using Microsoft Visual Studio Code, which is available for Windows and Mac systems. One thing I would like to emphasize is that I have underlined the word code, because there are two different types of Visual Studio that are being retailed by Microsoft. There's the Microsoft Visual Studio, which has a separate use, and the one that we would like you to download and use is the Microsoft Visual Studio Code, and it's been given by this special icon or logo here with the unclosed loop, so to speak. We'd also like you to ensure that for this course that your version of Python is up to date. We are aware that some users will have Python 2, which is an old version of Python and is no longer used. As technology evolves, you also need to make sure that your Python version is up to date. And for that reason, we'd like you to ensure that you've got the latest version of Python 3 up to date, and we will be discussing that element briefly in the next section when we start programming our code. But until then, we are going to be discussing the first elements of Python and being able to write our own hello world message. And also I'd like you to pay attention to some special prizes along the way that you may be able to redeem. Until then, momentarily, we will see you soon. So far, we've discovered the reason that we would be doing programming in the first place. We've discovered a bit about the history of programming in terms of Python and the architecture of computers. We've also discovered the tools that we're going to need in order to be able to program. So, we're going to write our first program here, which is called the Hello World program. And when we run this program, and by that I mean we're going to get the computer to execute the instructions that we want it to execute, we're going to get the hello world message printed out onto the screen. Now this hello world message is often attributed to one very famous computer scientist called Brian Kernighan during his work in 1974. This is Brian Kernighan today. He came about with this tutorial when he was writing his introduction to the language B, which then gave rise to the language C. And that is a language that many of you have either had the fortune or misfortune to work with. Over here on the right hand side of the window, I've got the Visual Studio Code program open, the IDE that we're going to use. Now, so this is the screen that you'll get to once you've done all your customizations. But before we start with any Python, I'd like to introduce you to one area of Visual Studio Code that you may find very useful in the future. And that is the Extensions tab, which you can get by Shift-Command-X if you're using a Mac. Now, the extension that I would like you to install before you start working with any Python is Microsoft's very own support for Python applications, which is otherwise known as, well, Python. That's all you have to write. The way you get to that is, of course, by looking at the search bar and typing in Python. Any case is accepted. Clicking on the tab over here gives you some more information about the Python extension, and pressing install over here will actually install it for you. I'm going to exit this tab here, and I'm going to unclick the extensions tab to get back to where we started. To begin writing a program, we first need to create a file, and that can be done by either doing the Command N or by doing File and New Text File. So, what I would like to do, just because as you can see, I'm using a very, very big monitor, which means that this text is going to be a bit small. And to increase the size of the text, I'm going to be doing Command and plus. So, first I'm going to type the message that we were due to write, and we're going to start with the print keyword and some parentheses, and then I'm going to type hello world, closing it with a parentheses. Now, as we're using the Python programming language, we're going to have to go through a set of instructions to tell the computer that this is a Python file and should be treated as such. To do so, I'm going to press Command S to save the file, and then I'm going to probably just put it on my desktop, and I'm going to give it a name, which is, for example, hello world.py. The .py is essentially, as you can see here, is known as the file extension. It tells the computer what type of file that it's expecting to work with, and it makes sure that it runs the appropriate instructions when the program is run. And then I'm going to press enter, and as you can see, it will ask me for some permissions if you're using a Mac. The main point that I'd like you to see here is that we've got the Python language set up, and the extension that we installed earlier gives us some more flexibility in terms of running this file. Now, if I press this play button, which tells us that we're going to run this file, we're going to get something called the terminal. And this terminal is essentially a window to our shell that we spoke about earlier. It helps us to interface with the heart of the operating system. Now, there are going to be some things that you may not see before. For example, if I just zoom out, we're going to get a couple of lines here. If I just run the program again, the first line here is the version of Python that we're using. And this over here is the location of where our file exists. This over here is just the name of the machine that we're using. So I've created a new account called Imperial Blockchain Group to be able to do the tutorials, and it's run under my machine when I'm using a MacBook Pro. So when I've run this program, the heart of the operating system has essentially returned back this message here called hello world. This is exactly what I was intending. And this is going to be a common theme for when you run your Python programs. There are also other alternatives such as the Jupyter Notebook, and while you are welcome to use a Jupyter Notebook for your own needs, if you've ever experienced it before or used it in prior studies, I won't be focusing on it so much, as I feel that the best way to be able to learn Python is to do it the old school way before we develop into other ideas such as using Jupyter Notebook environments, but you're welcome to use so at your own pleasure. Turning back to the presentation, we're going to discuss a bit more about the Hello World program that we've just created. If we look at the program itself and we dissect, or otherwise known as parse the program, we're going to get different features here. The print word that we suggested at the very start is otherwise known as a function keyword. We're going to be discussing functions later towards the end of this course, or rather, the end of this lecture in the first part of this course. The word hello world encapsulated within these speech marks over here is known as a string. And a string is essentially just a collection of different characters that we've strung together to make a set of words which are otherwise known as a sentence. And if you ever need to write a string, you must remember to include the quotation marks. As you'll see momentarily, much of Python is case sensitive. So if you have to write a piece of code which involves some sort of feature that Python has and you want to use it, you have to remember to spell it correctly and also make sure that it's used in capital case or lowercase appropriately. Uppercase was also what you can refer to. By that, if we look at a few examples, here for example, capitalizing the P in print will not run anything because the P has to be lowercase. So capitalized P in print is an incorrect use of code. Alternatively, if you don't include your brackets and you extend your string quotation marks to be outside of the brackets, you're not going to be able to run this code. Strings must be inside the brackets provided. And these sort of rules that you're going to get used to in the Python programming language are what we call the syntax. And syntax looks like a very unusual word, but it's also the same word that you would describe, very similar word actually, that you would use to describe the grammar of English. Sometimes it's also referred to as the English syntax. Very rarely, but syntax is more often than not used to describe programming. Essentially, the grammar of English and the syntax of programming are identical in terms of their meaning. So we've so far been able to write a program, but that's not really helped us in order to be able to store the information, because once we write that string, the hello world string, it's going to disappear and we won't be able to save it for any future use. How can we save some of the information that we're working with for future use? Well, essentially in Python there is an idea of using something called a variable. And what you do, and I don't know if my cursor can see this, but I'll certainly try. Excuse me. I'm going to use a pointer here to be able to highlight what I'm going to say. The string over here is the hello world string, and the variable that we attach it to is what we've given the name my string. So when we print my string, we're going to be printing whatever the value of my string is, or whatever's been attached to the variable, and it's the hello world string that we've given it. So when we execute this program again, it's going to print hello world for us. If you don't believe me, well, let's go and have a look. So we've already got this string over here, and as much as it would be quite nice to save it, we can't save it right now because it's quite volatile. The moment that we shut this program or actually want to work with the string and edit it or something like we're going to see later on, we won't be able to do so. So I'm going to rewrite this program. As you will see from the slides that we've just seen, I'm going to write the whole string again. Notice that I haven't used any parentheses here because I'm not using a function, and we'll come on to that again later in the session today. Now, I would like to print whatever's attached to this variable, and all I need to supply is the variable name itself. And notice that the Python extension that we installed earlier has actually helped us to do some auto completion. So it will be helping me to complete the name of the variable without actually having to type it out in full. Just to show you that again, I'm going to type my, and it's going to give me some suggestions, and all I have to do is press tab on my keyboard, which is just underneath and to the left of the 1 key, at least for my Mac. It also gives you some more information here in order to tell you what you're working with, and we're going to come across some of these parameters and what they mean later on. What I'm going to do is I'm going to save by doing File, Save, and then I'm going to run this program again. So it says run Python file. I'm just going to zoom in again here. Again, it's also printed hello world again. Just to prove that this is not the same as the original program that we created earlier without the variable, I'm going to do hello world 2, which does much the same job. Returning to the slides now, we're going to discuss a bit about what we've just seen and how to evaluate the features that we've just discussed. Variables have a job, and that job is to store certain information that we've given to the program or we've written in the program so that we can use it later, as you'll see momentarily. One way that I like to think about the idea of a variable, if you're new to it, is basically you've essentially got a little box and you've chucked something into the box. In this case, I've chucked in the string hello world, and I've put a very big label here and written out my string. So the name of this box is my string. It's my variable. When I create the variable myString, this is a process that is otherwise known as initialization. Some of you that are more advanced users will be familiar from previous languages the example of variable declaration, or you might read that if you're troubleshooting your issues online. I want it to be clear to you that variable declaration and variable initialization are not the same thing. They are completely different concepts, and Python does not support variable declaration as far as I know, but it does support variable initialization as you've seen above. And even if you come across the idea of declaration, please try to avoid using it, as you need to be quite aware of what you are doing in terms of the program that you're writing. It's also a good idea to think about how you are naming your variables, because you can give any sort of name to your variables, but it is important to follow a certain convention to make sure everybody else follows the same path. It's a bit like in chemistry when you have to name organic molecules in the same way so that everybody is aware of the standards so that no two people are confused. Of course, there is a bit more flexibility in writing computing science variables than there is in organic chemistry nomenclature, but please try to make sure that you follow a certain structure, as you'll see over the next few minutes. This is the program that we wrote earlier, and it's got some styling here. So the first word is lowercase, and the second word has the initially capitalized word name in the string when we've concatenated the string and declared it. One thing I'd like you to remember is to always be sensible with the name that you give, because obviously other programmers like myself or anybody else may have to look through your code, and if you've given it some very silly names, then that's not going to be very helpful to the team around you. In Python, there is a rule that you cannot start a variable name with a number, so try not to, because the program will tell you to get lost. Of course, as you've seen with the previous box model, this is my string, which is a variable that contains the hello world string itself. As I mentioned, the first letter of the first word in the string name is lowercase, and the first letter of the second word is capitalized. And that's otherwise known as camel case, because if you've ever been on a camel, it's sort of the back of it is a bit lower than the head. So we capitalize the head and the back of it is in lowercase. At least that's how I like to think of it. So camel case, for example, can work here. Lowercase in the first word, uppercase in the second word, first character. You can also, you're welcome to use an uppercase for the first letter of the first word, but I wouldn't recommend so. It's not something that you'll see very often. It's probably best to stick with convention. We've just been able to use strings, and which is made up of letters, in order to declare a variable. But that, of course, is not the only type of variable variable type that you can include in a variable. You can also accept other types of information, which is otherwise known as a data type. Here are some examples. We've so far discovered a string, which is like our hello world, which is basically just a collection of letters, numbers, and other special punctuation. An integer, which you're more familiar with maths, and maths is a common theme in computer science, as the two are very heavily interlinked, is just using a number. And this number can be positive or negative, which is basically what we mean by a signed number. So it has either a positive sign or a negative sign, but it has no decimal digits. It's a completely whole number. A float is a positive or negative, again, also signed number that does have decimal digits, and that might be quite useful later on. And of course a Boolean, which is something that you might be more familiar with from Boolean algebra, but it only gives us true or false values. Most of the time we will be working with strings and integers, and I'm going to show you some examples on the following screen. So, we're not going to be running this code here, but I'm just wanting to show you a bit of an introduction, because you can print any of these variables to screen, any of the variable types, and you'll get the same result. So I'm going to do my integer. I'm going to call it 49. As if you're an Arsenal fan, you'll know why that might be the case. And you can also do a my float, and I'm going to give it a useful float to say 3.14, which I think most of you are familiar with. My Boolean is going to be, well, in this case, let's try false. Why not? True and false, two different values. And if I wanted to print any of these, not that I'm actually going to do them, you can just do print my float, and there we go. And you'll probably see that it's going to print 3.14. Actually, you know what? Why don't we see what happens if we do print it? So I'm going to save it, and then I'm going to run it. There we go, 3.14. What a surprise. That is, of course, how the variables work in relation to the print function. The float is actually quite important if you're going to be working with financial markets. Have a think why. Think about currencies, think about FX, and think about the quotes that you get from the market. How are they presented? Are they presented in whole number integers? Are they presented in sentences such as strings? Or do you think they're presented as Booleans? Why do you think float might be most appropriate for that job? Now, I mentioned earlier that a lot of computer science has to do with maths, and in fact you can do maths with computers. Not really a surprise. As I said, they're very well interlinked. Here you can see the variable x that I've declared here stores the result of 3 and 5 with an operator in between. I want you to have a guess at what this result might be. When you have an asterisk here in the middle, or a star, which is much more easy to say, this means multiplication rather. And the result of multiplying 3 by 5 is, of course, 15. So the result that I'm expecting to print to the screen is 15. Hardly a surprise there. Now, other operators are also available in Python, and you're welcome to have a look at these yourself. So you've got the add operator, subtract operator, divide, multiply, exponentiate, and one that's quite funky but very useful is the modulus operator, which actually just gives you the remainder of a division. You can also combine operators together, which is basically the idea of BIDMAS, but you have to also remember that there's a certain order in which operators can work. So just remember to make sure that BIDMAS is respected when you actually perform your own calculations. So just to give you an example, I'm going to create this new file called datatypes.py. I'm going to try a little bit of maths just for our own entertainment. So to create a new file, I'm going to do new text file. It says select a language. Maybe we could try that actually. See, to be able to select a language straight away, all I have to do is go through these many different languages and end up with Python. And that's actually the logo over here. What I can do a bit better if I try again is select language mode, and there's a little search bar here, and just type in Python. So I'm going to first is going to be a good idea to save it. So datatypes.py. There we go, in full camel case. I'm going to start with the initial example that we saw earlier. So x equals 3 times 5, and print the value of x. Now, before I actually run this, before I run this program, it's going to be a good idea to actually clear out some of this stuff here on the bottom of the terminal, which interfaces with our shell. So To be able to get rid of something in this terminal, I'm going to enter a command to the terminal, through the terminal to the shell. It's the clear command. What it does, it just helps me to clear out the screen so I can see what I'm working with at my own convenience. So that now when I press play, it's going to print the value of 15. Fantastic. Now, what can I do? Let's try 3 minus, let's try it in order. 3 plus 5. 8. Fantastic. 3 minus 5, which I hope most of you are aware is minus 2. Fantastic. Now 3 divided by 5, I believe that is 6 over 10 or 0.6. Fantastic. Exponentiate. 3 to the power of 5. It's going to be 3, 9, 27, 81 or 243. Fantastic. And this one here, this new operator that you may not be aware of, is the modulus operator. And what it does, it tries to divide 5 into 3 and it spits out the remainder. So you get the remainder of 3. Now, modulus might not seem inherently like a useful operator, but it does have its uses. For example, if I want to check that a number is even or odd, why don't we try, for example, 15 mod 2. Now, because 2 doesn't go into 15 a whole number of times, it's going to print out a remainder of 1. There we go. And later on, you're going to see that we can actually test or certain conditions when a certain sort of value has been achieved. So, for example, I can test any number just by doing the modulus of 2. Likewise, if it was an even number, for example, 14, the modulus operator returns the value of 0, which is quite useful later on when we're doing some testing of numbers. I'm going to return back to the slide here, and we're going to crack on with a bit more of an understanding of comments. So far, we've written a fair bit of code in order to be able to perform some arithmetic, or to be able to print some strings or some numbers on the screen. However, there might be some cases where you might be having to revisit your code a year after you've written it, or you might have to deliver your code to another member of your team who may not be familiar with the way that you've coded the program. For this reason, it might be quite beneficial to actually add some notes to the program to make sure that everybody is on board with what the program is about, or to help remind yourself about what you've written a year or two ago. To do this, we're going to use some comments, and these comments are going to be helpful to us to help track what our code is doing. As I've mentioned just now, it's very important that you know what your code is doing, because if you have to edit your code or have to troubleshoot some errors inside it, if you don't know how your code works, you're going to find things a lot more difficult than if you could just simply take care in logging and programming your notes. As I said, you should definitely take some comments that will help you add some notes to your code, and this is normally done using the hashtag symbol that you can see. Normally on the Mac it is the Alt 3, but on Windows I believe that there is a hashtag symbol available. If we ran this code above, we would get the answer of 42, and that's quite significant because this means that the comments don't actually have any value when they're executed. They don't actually execute at all in Python in this case, because the comments are specifically just for our use. So the program, the Python program itself, doesn't actually interpret it as any runnable code. We'll have a look at it right now, briefly. So this is obviously the code that we use just to show that the number was divisible by the modulus of 2 and was therefore even. So maybe if I have to sort of justify this code to somebody that might be on my team, I might need to write a note for it. So I'm going to use the pound sign over here, and I'm just going to write divisibility for evenness. Of course, I'm not sure if that's the correct terminology, but it seems to work quite well. And I'm just going to write one more thing, print the result to the screen. Two very simple comments, but they have extremely useful value for when you're trying to troubleshoot your code, when you're giving your code to somebody else on the team, or simply trying to revisit code that you've written a while back and you need to remind yourself what it actually does and what it serves to do. Of course, if I run this code, this will give the value of 42, and as you'll see here again, if I run this again, it still gives me the value of 0, which is what we were expecting. And of course, it's good practice to clear the terminal when you are doing a new task. And as you'll see there again, it still runs the program and returns a value of 0. And to sort of show this, if I did, for example, reassigned the variable, so x was equal to 15 modulus 2, of course, it's only going to print the line number 2, because that's the only line that hasn't got a comment to it, hasn't got a hashtag in front of it, and that's going to be the variable x that we're going to be printing. And conveniently, the IDE has shown that through the highlighting over here, as you can see on line number 2. So if I save that and run it again, it's all going to give me 0 here as my desired answer. So nothing too complicated over there. As I said, comments are not executed, but they have their uses. For example, if other programmers require to your code and they would like to have an idea of what you've written, or when you open your code after a long time. We're not just going to be able to just do maths, because that would be quite simple and would be very limiting to our potential abilities in using a computer. We could actually compare values between two different variables in order to justify some sort of procedure. To do this, we're going to use something called relational operators, and they essentially compare the value of two different items that you provide. In this case, we're going to provide the value of two different variables. Now, when I mean relational, it sort of looks at the relationship between the two operators. It looks at where two different variables, my apologies, and it looks at whether one variable is bigger than another, one variable is smaller relative to another, and that's where you get the value of relation or relative. Here are some relational operators that you will encounter, and you must take note of the fact that they have a specific sign and order to which they are written. When you use a relational operator, the result of using it gives you a Boolean value, which is either a true or false value. And I'm going to show you one example over here. So this is an agechecker.py program that I've written, and it checks to see whether the age provided is of legal drinking age. So if we're going to write this program in IDE here, so I'm going to press Command N this time, just for the brevity of the shortcut. I'm going to save my program as agechecker.py. And first of all, of course, this is just for repetition, so I'm going to check whether the age is legal for drinking alcohol. And by that, of course, if we're in the United Kingdom, that's greater than 18. But as far as I'm aware, if you're in America, you have to be older than 21. So my age is, of course, well, let's say we're 21. So legal drinking age in the UK is 18. So let's print a message to the screen. Is my age greater than legal drinking age? Now we're going to try and evaluate this expression here. So print the result of my age being greater than legal drinking age. And the result of this print function is either a true or false value. So just to check that, we've saved our file. We need to just clear it just for clarification, and we're going to print hopefully true. That is in fact correct. It is true that my age is greater than legal drinking age. Normally we don't actually use Boolean values in their raw form. We use it later on when we're going to do something called selections and if statements, and that is the topic of the next slide, as you will see momentarily. We've written the code and it's executed from top to bottom in a Python file. This sort of code that is run from line by line from top to bottom is known as a sequence. Computers, however, are much more advanced than just using a sequence. They can also evaluate certain conditions and run the code appropriate, and this is otherwise known as a selection. When we use selection, we're essentially having control over where the program goes, and this is otherwise known as the program flow. And when we have control of the program's flow, we obviously call it flow control. To achieve flow control, we're going to use three specific keywords, the if, elif, and else keywords, to gain, respectively, the ability to use if, elif, and else code blocks, respectively. A code block, in this context, is simply just a collection of lines of code which form to make a block and have some sort of relationship to one another. When we use code blocks, it's important to make sure that the indentation is vital, because if we don't indent, the Python interpreter will simply tell us to go away and fix our code again with lots of errors instead. The first type of selection that we're going to cover is essentially the if statement. Now, to understand the if statement, you first have to understand the initial condition and the variable that it is assessing. If we look at this code, for example, we've got line number 1. This is obviously a comment and it doesn't execute. If we look at line number 2, we've got a variable called mySubject and it's given the value chemistry. If mySubject is equal to the value of chemistry, and this operator, the double equal, checks whether mySubject is identical to chemistry, and it's both a string in both cases. So if mySubject does contain the string chemistry, then we're going to print the string your subject is awesome. Irrespective of whether line 3 is true in terms of the condition, as we saw earlier, line 5 is always going to be printing because it doesn't form part of the if block. The if block is between lines 3 and 4. We have our condition and we have the code that we wish to execute. The overarching result is that we print out the following two lines: your subject is awesome and IBG is the best. Two statements that are inherently true. Note that the first line would only execute if mySubject was equal to chemistry. So line number 4 only works if mySubject is indeed equal to the value of chemistry, the string, and it has to be indented in order for it to work in the selection. So it has to be shifted to the right. We look at the following example here that I've written. I've adapted the age checker code that I wrote earlier and sort of made it a bit different. So I've declared a variable called myAge and I've checked if it's equal to 18. This is the condition that it has to meet. If my age is greater than or equal to 18, and as far as I'm aware in this country, if you're 18 or above, you can legally vote, and that is what it's going to print to the console or the terminal over here when we run the code. There we go. So you can legally vote. If it was, for example, 17, nothing would be run. You see, no message means that this condition isn't true. It returns false, and if the condition here is false, this line or the following lines will not run. And that's very straightforward. It is quite important that we understand what our if statement is doing, or rather what our if block is being executed. To do this, we're going to draw decision flowcharts out to be able to map out the specific selection process that we've been using. And when we do this, this is otherwise known as an algorithm. An algorithm essentially tracking a set of decisions that we make in order to get to a final result. In a lot of computer science theory, this is the sort of algorithm that you'd be drawing out as a design flowchart. So we start at the very top here, with the start command, and this essentially feeds into this decision key over here, whether the subject is chemistry or not. And if it is, we're going to follow this loop here in the clockwise fashion, going from right all the way to the bottom. And even if the subject isn't chemistry, we still execute this string to be printed to the screen before we end the program. Now these shapes are all very unique, and they have a specific use in the context of decision flowcharts for algorithms. As you can see here, the rounded rectangle denotes a start or end, and this diamond over here, which is essentially fallen over square, denotes a decision where we have to actually specify which leg of the decision is going to go into which direction. And these parallelograms, or fallen over rectangles as I like to think about them, is essentially data input or output. So far we haven't actually inputted any data, and it's very rare that you're going to be involved in writing inputted data to the computer where you enter some information from the user and it has to evaluate that information appropriately. Instead, we're going to be using some data output, which is basically us printing the text to the screen, as you've been used to for quite a while, and we denote that with a parallelogram. So far, we've looked at the idea of if statements, and as part of our selection processes, we were able to draw flowcharts with a specific key attached in order to understand the selection processes involved. However, we can extend if selection to include other sorts of components, such as else clauses, and the idea is that we choose an alternative output based off the input that we add into the program. Look at the following code, for example, and I will be the first to admit that I've sort of fallen out of favor with this sort of example. That is very Imperial tailored, so there will be a more generic example which suits the case much better. We look at the following example in the meantime on the slide. We have the condition that if my subject is equal to chemistry, then we would print that your subject is awesome. However, in this scenario, we have an alternative subject that's not called chemistry, it's maths. As a result, we don't print your subject is awesome, as you can see on line 4 over here, because my subject is equal to maths, and our condition isn't met on line 3, so instead we print the output that's given by the else keyword, rather the code block actually itself, and in this case we print Imperial is a smart place to be. Notice that if my subject was equal to chemistry, we'd only print out this condition and not this one, and that's predicated on the idea of using the else keyword, either this or that. If it's this, do this, else, do this, do that instead. It's very sort of linear in terms of its compatibility with real-life English. So instead we print out the following output. Imperial is a smart place to be. We use a specific type of keyword here, which is the else keyword, and it's actually known in programming as a clause. The idea of a clause in English grammar is that it requires a primary component for it to work. In this case, the else keyword only works if you have the if keyword before it. You can't just use an else keyword on its own, so essentially you need an if statement in order to use an else statement. My apologies. I've written a file over here called ifelse.py, and I've imagined that I am running a funfair ride and that I have to work out the price of an admission ticket given a certain age. I've also given two specific conditions here. If the age of the individual is less than 11, i.e. they're 10 years or younger, they can go on the funfair ride for free. Purely hypothetical, of course. If they're not less than 11 years old, then they're going to have to pay a £10 ticket as their admission fee. It's quite simple actually to be able to write the sort of if-else structure for this sort of scenario. If the age is less than 11, we print you can go on the funfair ride for free. Perfect. Alternatively, if they are not under the age of 11, then they're going to have to pay the £10 admission fee. Now we could just do else here, although some of you might be thinking that it would be something like if age is greater than or equal to 11, print something. And that does work, which in theory it does if you get it right, but actually the catch all is the else keyword, because if the age isn't less than 11, then they're going to be 11 years or older, and every other scenario would be covered by the else keyword. So we're going to print you must pay the full £10 admission. Save that. Think about running it. Notice the terminal is completely clear. So have a look. Wow, you must pay the £10 full admission. That's because the age is not less than 11, just to prove my point. The age was around 5 years old. Well, you can go on the funfair ride for free. And if you're much older than that, and you know, older people still enjoy fun fair rides, say the age of 30, you must pay the full £10 admission. Say my age, probably 23, quite an old person myself. You must pay the full £10 admission still. So that sort of gets the idea there. And just for people that are a bit less convinced, if it's 10 is less than 11, on the fun fair ride for free. One thing that I like to just add before we move on, as quite a little gimmick, is this extension here that I've installed earlier called In Your Face. If I just minimize the screen a bit just to be able to show it on screen. This little meme over here will track how many errors you've got in your code. So right now our code is perfect, but if we introduce an error, for example if we remove our colon, it tells us that we have one error. Of course the IDE tells you using this underline where the error is. We try and include another error. That'll be 2, maybe one more, 3, hopefully. And yeah, just hasn't picked it up. Point is though that it does pick up the number of errors, and progressively it would print out some pictures of a very meme-like nature based off the Mr. Incredibles meme that you may have seen recently. Just thought it would be quite fun to show you. Now if we head back on over to our code and our presentation. Of course this scenario only works if we have a binary selection process. Either we have a process of 2 different options that we can select from. We may have further conditions we want to test. What if our student over here in this example is a mechan student? Of course, mechan students have it very tough at Imperial. Not sure why you'd want to be the mechan student at Imperial, but different matter entirely. The point is though that we have another condition that we'd have to meet. Just like in our previous code over here, if we head on back over, what if the age is greater than 65? Maybe maybe there is a special plan that we put in for seniors to be able to enjoy the fun fair at a discount because they've got their own pension. To include these sort of third degree conditions, as I'd like to call them, just because it's not the primary or the catch-all exception case as a sort of intermediary case. And that would lead us quite conveniently onto the idea of an ELIF clause. The ELIF clause, if we have the example shown up over here, covers another option that we haven't selected in our primary condition. Of course, my subject is still maths, so it doesn't fit the chemistry situation where your subject is awesome. Of course, we're not going to be wanting to print out this line over here because we're not studying mechanical engineering, so our subject isn't tough, so this isn't going to be printed. We'll still be printing out Imperial is a smart place to be. Of course, that's not a surprise, it's the same situation as before. However, try it for yourself. If you typed in mechanical engineering as your my subject value and tried printing it, you'll get the output given on line number 6 that your subject is tough. I'll leave that to you to find out for yourself. The ELIF is otherwise known as a contraction of the phrase else if. So if I have this condition, do this. Else, if I have this other condition being met, then please do this. And if that doesn't happen, else, just do this. So if, do this, else if, do that, or in all other cases, all else, do the final catch or exception. It only executes, of course, if the previous statements are not met. So you can have many ELIF statements, which you are allowed to do in Python. You can have more than one ELIF after a primary if. So you can have one if, as many ELIFs as you want, and one else. Sort of makes sense. The primary condition, sort of intermediary conditions in plural, and one catch all exception where none of the conditions are met and you have to force out an output. If we head on over to our code over here, I've pre-written this actually just to save you a bit of time. So I spoke earlier about the fact that if we have a senior individual, we would have to offer them a senior discount of 10%. Now, of course, we have 3 different possibilities that we could be able to test. So why don't we try and test some? If we clear the terminal over here, connect it to our shell, so we know that if the age is, say, 9, we could go on the fun fair ride for free. If, of course, the age is around 15, we have to pay the full £10 admission. And likewise if we're 30 or 40 or 50. However, if we are a 65-year-old, we wouldn't have to pay the full fee. Instead, we can receive a senior discount of 10%. That doesn't matter if we're 65 or 85, for example, because it's greater than or equal to 65. Of course, this little extension here does throw an error while you're editing some variables, but as long as the final outcome is still satisfied, then you're in perfectly good shape. Fantastic. Now, if we can crack on, we'll move on to the next section. The idea of nesting is one that you will commonly see, and you'll have to consider the idea of nesting in some situations where you need to further clarify your conditions. If we look at our Imperial subject ratings program so far, that's a new term that I've given it. We've now changed our subject to mechanical engineering in line 1. Now I've also included another parameter, which is the year of study. So since we're doing mechanical engineering, we're going to be between lines 5 to 9. I know that because line 10 is an else, which doesn't satisfy our requirements, or it's not rather printed. Of course, if we are in year 1, if you're a mech eng student in year 1, you can print out to the console that life is very fun for you, because you haven't experienced what mech eng really is. If, however, you don't study mech eng in year 1 and you're a second year, third year, or by Jove, if you actually manage to survive through third year and you've still survived into your fourth year, you'd print that your subject is tough. So this would be satisfied, this would turn true, except we wouldn't be able to satisfy this if statement inside a previous elif selection keyword. So this sort of selection isn't nested inside the elif here, so we would be printing out the else keyword or output, which is that your subject is tough. Indeed, that is the result. The idea of this whole structure, as I've said, is the idea of nesting. So an inner statement, if statement, or an if structure is essentially wrapped or contained within an elif clause. And that's what you can see over here. Just on the spot here, we could try that over here. So let's think about certain sort of parameter that we might be considering. We consider the idea that say elderly people have a height. If the height is less than 170 centimeters, we could include a senior discount of 10%, but in addition, we could actually print out something about their height. So if height is less than 170, and that's just an arbitrary number, we'd print you are too short for this ride. That's just for elderly people. Nothing against them. Some of them are some very lovely people. Else, print you are still tall enough to go on this ride. According to human anatomy, as the people get older, they tend to get a bit shorter. That's just the premise of this sort of idea. If we clear, so we have a age of 85 and we have a height of, let's say 170, let's try 160 just to be a bit more precise in terms of our conditions. We run this code over here. Not only do they receive a 10% discount, but they're also told that they're too short for a ride, or some rides rather. I'll just change that over here, some rides. However, if the height is around 180, so they are still staying on strong and still able to walk at the ripe old age of 85, which is fantastic. They're still tall enough to go on this ride. Very well done. So not only have we been able to do a selection process based off the age, we've also been able to do it based on the height over here. And that's the point of it's a bit of nesting. So the next section we're going to talk a bit more about the idea of looping. And in looping we're going to be able to essentially run a condition and then be able to execute code repeatedly until our condition is met or until it no longer exists. And you will be back. So far, we've seen that with selection processes, we can define a certain condition and be able to extract a certain output once a certain condition has been met, and that's only possible for one of a given selection of conditions. However, we could actually repeat a specific selection over and over again until a certain condition has been met, i.e. until we are satisfied. And the idea of this, it gives rise to something called iteration. And iteration is something that we commonly achieved with numerical conditions, as you will see momentarily. If we look at the flowchart here on the left, we start on the left-hand side with x equals 0. And if I just revert to my laser pointer from earlier, we start with x equals 0 and print it out onto the screen. Given that x is 0 and it's less than or equal to 5, we then go through this sort of chain of events where we add 1 to x, so 0 plus 1 is 1, and then we print it onto the screen. So 1 would be printed. Then, given that 1 is less than or equal to 5, the same process repeats. 1 plus 1 equals 2, so we print 2 onto the screen. 2 is still less than or equal to 5, so we still print it onto the screen. And you can understand what would happen for 3 and 4. And actually, if you think about it, 5 as well, because once we've printed out 5, is x less than or equal to 5? That's still true. So we print out the value of 6 once we've added 1 to it. So we'd get 0, 1, 2, 3, 4, 5 and 6 printed to the screen. And is 6 less than or equal to 5? Certainly not, so we terminate the program. We can obviously remind ourselves of the flowchart key, just for your personal benefit. We repeat this idea again. We look at the loop that we've just generated. We actually look at a loop with no open ends. So I can show that by drawing this little circle here for your further convenience. It's otherwise known as a closed loop, which is why iteration often has the term looping. And if we look at the result that we'd get from this sort of flowchart, we'd get something like this. We start from 0 and end up at 6. In programming, there are often two types of iteration, for loops and while loops. We'll talk about for loops first, as it sort of explains while loops a bit more succinctly later on. If we look at for loops, for example, for loops can only allow us to iterate a certain number of times. And because we know when it's going to end, for definite, it's what we call a definite loop. We know when it ends for sure, or for definite, essentially. If we look at this example here, that's very similar to the example that we had earlier, except we are just printing the numbers in the range between 0 to 3. That's what gives rise to this code over here. We use the range keyword. The range keyword, essentially, as you will see later, is a type of function where it stores all the numbers from 0 to the value that you provide, but not the actual value itself. The number that you pass is what we call exclusive. It's excluded from the final list, which a list we also come across momentarily. If I sort of show this code in terms of what it shows onto the screen, this is what you'll expect. So the range will give out numbers 0, because it starts from 0, 1, because that's still less than 3, 2, because it's still less than 3, but it doesn't actually include 3 itself. If we actually go to the code from earlier, so we'll find a file called forloops.py. So we're first going to need to print all the integers from 0 to 6, inclusive, but of course in Python we're going to have to consider that a bit. So print all the integers from 0 to 6 inclusive. I'm going to try and use the range function as I mentioned earlier. And as I mentioned, for I in range would be a good start, because as we saw, it worked with a range of equal to 3. Of course, 3 wasn't the number that was actually included in the list, and this sort of bio sort of tells you that a bit more. It's an exclusive thing. So it starts with an inclusive number, as you can see here, starts inclusively and ends exclusively, and you'll be reading about step momentarily later on. So if we want to print from 0 to 6, where 6 is included, we're going to have to try to increment by 1, so we go to 7. So we actually pass in the value of 7, because it still prints from 0 all the way through to 6. So once we've got the range, we're going to print I. We sort of play this over here. we've got 0, 1, 2, 3, 4, 5 and 6. Now, the idea of I over here is a bit unique and is something that you may not have seen before. So, just to recap, the number that we pass into the loop here is not included in the final result, which is why we call it an exclusive parameter, which you'll also come across later on in function theory. So, if we had a start and end point that we wanted to specify, that should of course be start and not stand, which will probably be reverted by the time this presentation goes out. We don't actually have to start from 0. We could actually start from another number that might be of interest to us. So, for example, we can start from number 1. If we do for I in range 1 to 5, remember 1 is inclusive as you saw in the previous example, whereas 5 is exclusive. It's not included in the final result. Have a think about what these numbers might be that might be printed out onto the screen and come back in a few moments. So, as I've just explained, 1 would of course be included because it's an inclusive starting limit or starting integer, and 5 would be exclusive. It's not included in the final values. Printing that out on the screen, we get the numbers 1, 2, 3 and 4. And of course I alluded to the idea of this sort of spooky variable called I. What does I actually do? What we call a counter variable. Essentially the loop only works if we're working off this variable over here. So for any numbers that we specify in a given range, so a range of numbers, we assign them to the value, the value 1 through to 5 to the variable I. So when we start, essentially what we're doing is that for a number I that we have specified to be looped through the range of numbers 1 to 5, we print I. So when at first we have the range has the value of 1 right at the start, I is given the value of 1 and it's been told to be printed to the screen. Then we loop through to the second number, that's obviously number 2. Then I becomes 2 and is printed onto the screen. So we can sort of see the circular nature that I'm drawing out. When I is equal to 3, we print it out onto the screen by setting I equal to 3 in the first place, and then all the way through to 4, because remember 5 is exclusive. And of course it doesn't have to just be I, it could be J, K, AB1, C1, 2, 3, as long as the variable name didn't exist before the loop. Of course I can show you that here, you just have to remember that it matches. So for IBG in range 7, print IBG. It will do the exact same thing as before, as you can see there. For Imperial, whatever. For Imperial in range 7, print Imperial. Not sure why you'd want to do that, but it seems to work for some people. There you go. And just to prove that I haven't just sort of dug out an old code, if we print Imperial in the range of 9, we get up to 8. Of course, 9 is not inclusive, it's exclusive. But anyway, that's a simple example there, just to show you how loops work without any of the faff. We previously saw the idea of having an if statement inside of another if statement, and we called it a nested sort of selection process, or a nested if statement. We can also have the idea for nested for loops. Essentially the question is, can we have a loop inside of a loop? And the answer is yes, and that is very useful because it helps you save off a lot of repetition. Look at this code here, for example. If I just revert to my laser pen over here momentarily, we start with this line over here. Notice this is of course a comment, as I mentioned previously. We have an outer loop. The outer loop uses the counter variable x, and it counts in the range of 1 to 4, so 1, 2 or 3. The inner loop exists inside of the outer loop, so it lives inside, it's nested, and it uses a counter variable y in the range of 3, so 0, 1 and 2. And what happens is that x and y are multiplied and they're printed out for each iteration of the loop. So to go through an example, when x is equal to 1, we keep the outer loop constant, so x remains equal to 1, and then we start with y. When y is equal to 0, x multiplied by y, so 1 multiplied by 0 is 0. 1 multiplied by 1, because y is then equal to 1, because it's 0, then 1, then 2. So when y is equal to 1, 1 times 1 is, well, 1. X is still constant, because we still haven't finished this loop first, so x is equal to 1, y is equal to 2. 1 times 2 is 2. So we've done 1 times 0, 1 times 1, and 1 times 2. Then, once we've finished this whole loop and we've cleared it out, we then increase x by 1. So then x is equal to 2. So then we do the same thing all over again. Y is then equal to 0. 2 times 0 is 0. Then we do 2 times 1 is 1, because we increase our y while we keep x constant. And then 2 times 2 is 4. So 2 times 0 is 0. 2 times 1 is 2. And 2 times 2 is 4. I really do hope I've got that right, but I've at least managed to correct myself later on, thankfully. And then finally we then end up with x being equal to 3, and then doing the same thing over again, and x is equal to 4. Of course, we show that on the screen. We've essentially got the first 3 multiples of 1, 2 and 3, provided that we start from the index of 0. Well, say index, provided that we start from 0. Index, of course, is a loosely used term that we should be careful of in computer science, as you'll see later on. One way to be able to track the idea of nested for loops is to be able to look at the outer loop and the inner loop and then see what the result would be, see if you can evaluate it. This is a very good example of looking at nested for loops, as you can sort of be able to track the outer loop, track the inner loop, and then multiply the results, all the way from x equals 1 to x equals 3. Notice that 4 is obviously exclusive, and I'll keep on repeating that point repeatedly until it's well established into your thoughts. If you look at the example over here, and I emphasize the idea of an example, I'm going to be covering lists later on, but I just wanted to show you that using a list of lists, so basically nesting a list inside of a list, gives rise to matrices that you'll be commonly aware of in mathematics. And using a for loop inside of another for loop helps me to be able to total all of the elements inside the matrix and give out a total sum. In this case, I've run it for you prematurely, and it's given the value of 45. And so you can have that attempt at yourself to seeing whether this whole matrix sums to 45, but I'm pretty sure it does, and so does the computer. So, I've covered enough there for nested for loops, and for loops in general. While loops are essentially quite similar. In for loops, we said that the condition was for if there was some items in a given set, or in a given condition. For while loops operate in a similar paradigm. However, they only work while a certain condition is true, or while a certain condition is still valid. Look at the following example, much simpler example than some of the more previous stuff right at the very start. We start with x is equal to 1, and while x is less than or equal to 8, so while x is less than or equal to 8, if you remember your flowchart, we print x. And before we sort of reboot the loop and go around a second time, we have to make sure that we increment our value of x, so that then we get x is equal to 2, we print 2, x is equal to 3, we print 3, and so on and so forth. You have to remember, as you'll see in a moment, to include this increment at the very end of any while loop. And of course, if I showed you the output, we go from 1 all the way through to 8, because once we print 8, we get x is equal to 8 plus 1, which is 9, which means this inner loop is finished and it no longer works. In fact, it's a bit sort of redundant to call it inner loop in this scenario, because we haven't got another loop. I thought it would be nice. This is just after fact that I thought it would be quite nice to keep, because obviously we do make our mistakes quite a lot when it comes to looping. It's a common mistake that people make. Why do while loops tend to compare to for loops? Well, with a while loop, we have to be careful that while loops actually don't have a definite ending. They're known as indefinite loops. They continue to loop until a condition has been fulfilled, not while a certain condition is true, as for a for loop. Well, rather, to correct myself, while certain elements still exist that haven't been filtered in most cases. So if we start from the very top here, we start with x is equal to 1. We then go through to this sort of selection process where x is still less than or equal to 8. If that's true, then we print x, and then we increment the value of x, and then go around to back to asking the question over and over again until we get to x is equal to 8, print it, 8 plus 1 is equal to 9, and then this no longer works, so we get the answer of no. One thing I'd like to point out is that Python is one of the few languages, and as far as I've seen in my research, the only language that has while loops. It's an example of indefinite loops. Of course, I think you're pretty familiar with the idea of the output that we get from this sort of result. One thing I'd like to make you aware is that the incrementation here that you see in this part of the loop, so x is equal to x plus 1, is incredibly important. Because if you don't do that, essentially if we start from x equal to 1, x is equal to 1, and then we say is x less or equal to 8, it's correct. If we print that out, then without this incrementation, that x is still equal to 1. So we keep on going around. Is x less than or equal to 8? Yes. Print it, and then print it, and then print it, and then print it, because there's no increment that will help us to get out of this decision diamond, or decision tree rather. So once we've got to that point, we didn't have to completely be stuck inside of a loop unless we've got an exit plan. Sort of show you this in a bit of a diagram before we go over to the code. Look at the incrementation that's been absent now. So start with x equal to 1. Is x less than or equal to 8? Yes. But print x, but then we come back round. Is x equal to 1? Yes. Print it, come back round. Is x less than or equal to 8? Yes. Print it, come down. Because we haven't changed the value of x. You essentially become stuck in an infinite loop, and you remain with x is equal to 1 indefinitely. So we say that the loop isn't closed or it's never terminated. We'll see if we can try that on my computer for a moment, but of course please don't try this at home, as your CPU may not have a very nice day. So we're going to start with another file, and I'm going to conveniently call it while loops.py. In fact, we're going to look back at our flowchart and see if we can convert the code from our flowchart into a sufficient while loop. See if we can go backwards. There we go. So if we look at the code here, we start with x is equal to 1. So let's just write a comment here, while loop counting numbers. X is equal to 1. That's a good start. So we have to install this loop here. So if we just move over to the next line, so while x is less than or equal to 8, print x. So far we've covered this, that, and the loop itself, but we're missing this decision tree. Rather, we're not actually missing this decision tree, we're missing the increment. We have included the decision tree here. So x is equal to x plus 1. Of course, I think it's fairly obvious where we are going to go. So if we run this through, well, first of all, if we clear the model terminal, we might be able to see what we're doing. Of course, we can see we've printed from x equals 1, 2, 3, 4, 5, 6, all the way up to 8, including 7. If I clear this again and comment out this code, we're going to end up in a bit of a pickle. Because we're not incrementing, x will always remain equal to 1. And if I run the loop, sort of see by, if you look at the scroll bar here, this is a never-ending loop. I can never get to the bottom of it. And of course, those of you who have a Mac are aware that if you leave it for too long, the fans will go off. And that's certainly the case with my laptop over here, especially with an Intel i5 processor. Anyway, enough waffle there. If you are ever going to find yourself in this sort of situation where you've mistakenly started a while loop that doesn't end, you can use the Control-C shortcut to get out of it, which is otherwise known as a keyboard interrupt. That's at least for the Mac. I believe it's the same thing for Windows, and it disrupts the entire loop by throwing in a wrench, and it says essentially that there's a keyboard interrupt. So print x no longer runs because we have demolished or disrupted the code. But if I'm scrolling up, you can definitely see the number of number ones that are available on the screen. And in fact, there are so many number ones that I can't actually reach the top. So beware when using while loops that you make sure that you increment appropriately so that you don't get those sorts of problems, but just nice little programs like that you see on the screen. So I've already discussed this area here. Of course, it is possible to improve this bit of code over here momentarily. Sort of discussed that x equals x plus 1, sort of a bit redundant that we are having to repeat x all over again. Of course, if I'm incrementing by 1, then I've already taken the variable over here, evaluating this new value, and then reassigning it. So what I can do, as you can see here, that would be just a repetition of my term x. What I can do is I can instead use an increment operator. So essentially the plus equals basically tells me, so take this variable, add whatever's on the right hand side, and then reassign it. I sort of show you that here, just with a bit of reorganization. It's always a plus or equals in this case. I get the exact same result. Just to show that for the more unconvinced viewers amongst you, if I change it to 10, I'll also be able to get the exact same idea, but just going up to 10. So using this operator is very useful in order to save time and reduce your chance of getting errors by putting in the wrong variable name. Earlier we spoke about the idea of different data types, and one of those data types that we said we'd revisit later was the idea of a string. Well, we remember that strings were specifically characters that were put together to make a word or a sentence. And one thing that I alluded to, or I possibly alluded to, was the idea that strings are indexed. Essentially what I mean by indexing is that each letter or each character in the string has a specific number attached in a sequence so that we can access it later on. I'll show you an example here of a string of letters that make up the word Python. If we look over here, we have the letter P, Y, T, H, O, and N. Naturally, we could index or give a number for the position of these letters by starting from the left-hand side, i.e. starting from the left-hand side of the word, or starting from the beginning of the word rather. In this case, we could start by giving the letter P the value of 0, 1, and then 2, all the way up to 5. Now, so the observant amongst you might question why we don't just start with 1, and 2, 3, 4, and 5, and 6, as per normal ordering processes. And you'll see that later on there is a certain reason for that, in terms of the computational efficiency. Another thing that does exist in Python is the idea of doing a reverse indexing. So using a negative index means that we essentially give the last letter a -1. So in Python, often if you see a -1 in the wild, it basically means the very end of the string in this case, and then we go all the way up the way to -6. So we start with 0 here, but for the start positive index, but for the negative index we start with -1. There is a reason for this. So again, these are two different methods of indexing the strings which you are able to use, but actually to be able to extract certain information out of these strings, you have to use something called an operator. And an operator essentially works on a string in this case to get what you want. In this case, to be able to work with strings, we need to use a square bracket operator. The way this works is that we provide the string in question, and then we provide a certain value, and that extracts a certain character in this case. So if we do Python and then index the 5th character from the start, or the last character from the right hand side, we get the last letter N. And I will show you here using the Microsoft Studio IDE. So my string is equal to Python. I am of course going to be saving this, so string index.py. So my string is equal to Python. Print. That's what I think about printing. My string is equal to 5. Notice here as well that I can actually not just explicitly mention the string itself, but I can also mention the variable, which then is substituted with the value of the string itself to be able to extract what I'm requiring, i.e. the 5th letter starting from index of 0 from the left. And if I do so, I get the letter N. Just to be absolutely sure, if I just repeat that, what I can do once I have entered the clear keyword is I can press the up button to be able to get the most recent command that I've inserted onto the screen. And if I do the same thing here, hopefully the second command as well, the second to last command also executes the file as well. because it tells me that to use Python 3 to be able to run this file. So we've got my string with an index of 5 that prints the letter n. Likewise, as I mentioned, if I do -1, I get the exact same answer here. There you go, n as well. If I did -3, that'll be quite obvious what that letter would be. This here is my n is -1, o is -2, so h must be -3, as per usual. And to go from left to right, 0, 1, 2, 3, it's also the same number. So if I do my string equals 3, and then print that, I also get h. Going back to the slides, of course, we've been able to notice the exact workings of a string index. An often commonly asked question from people that begin the experience of Python is to often ask why strings are indexed from the number 0 and not from the number 1. The reason for this is that using a 0 offset again shows how far from the beginning of a string or from the beginning of an index that you have to travel. If we look at this Python string, for example, if we want to go to the letter h, we have to go 3 from the very start, because obviously 0, which is the very starting element, is occupied by the letter p. So to be able to get to h, we have to make essentially three different jumps to be able to get to h itself. Now, part of computer science and computer in general is about being efficient when storing arrays in memory. And one of the resulting ideas of this is that often memory is what we call contiguous, so we try to group things as much as possible and keep them as close to each other as possible and not keep them far apart. Keep the elements involved in the memory as far apart as possible. We like to keep them bunched up and as close together as possible. The idea is that by using a 0 offset, we can actually access, say, an element, well, I said the letter 3, letter h in the index of 3, but if we want to take, for example, get the letter t, all we'd have to do is, far simply, using a 0 index, work out the address, which is essentially much the same way that you have a home address for the postman to deliver your emails. We also have an address for where our first letter lies, the letter P, so that would exist at some address, and then we have to add on a certain extension to that address to be able to work out where our letter T lives. So we know that letter T lives 2 doors from P, and we also know the size of each character in the element, which is something to do with bytes, which I'm not going to mention in this lecture, but it's for your own personal reading if it interests you. And essentially it helps us to get to the letter T. So we do the address of P plus 2 times the size of the element, which in this case is a byte. If that interests you, please do read on about it. The problem is that if we do a 1 offset, so we start with a number 1 more than 0, we would still have to go for the address of the letter P, assuming it started at 1, but then to be able to get to the letter T, because the letter T is at the nth term of 3, we have to do 3 minus 1, which equals 2. That's 2, still gets us 2 doors down, multiplied by the size of the element. And the problem is, of course, is that using the n minus 1 introduces a subtraction term. And while the subtraction term doesn't really affect our calculations if we are working on this one operation, you can understand that a computer is doing many millions of operations a second. So it's wasting a million times. It's going to be doing this subtraction, and it's going to be wasting a bit of time, whereas it could be a lot quicker by using a 0 index and then just starting from the nth term provided to the letter in the index of a 0 offset index. Of course, we don't just have to select one character in question, we can select more than one character in a string. So if we include the starting and the ending index, like we did previously with range, we can also actually do the same thing with semicolons instead, rather than just with commas as you saw in the range function. The starting index, of course, is inclusive, again, as we saw previously, but also, similarly, the ending index is exclusive. It's not included in the final calculation. What you can do, if you wish, is you can also include a step function. So essentially if we start with 1, 5 and 2, we start with the letter y. we end with the letter N, but we take 2 steps rather than 1 step. So if I just get my laser pen out again, we start with the letter Y, which is at index number 1, and then we skip 2, we get H, then we skip 2 and get to N, but notice that N wouldn't be included because it's the final index. So if we did Python 1 to 5, simple, we'd get the letter Y, T, H and O, noting that N is exclusive. That's exactly what I've just stated. Whereas if we did the same thing, we just get Y and H because it selects every 2 indexes from 1 to 5, i.e. just the first and the third. I'll show this to you on the code here, so we extend our idea of string indexes. What I'm going to do is I'm going to comment out the previous code. Of course, you can just put a hashtag in front of both those lines, but if you're using a computer, you can do, especially using a Mac, you can do Command and A, which selects everything. That's Control A to you, and then you do Control or Command, and using the / symbol, I believe it's the / symbol, but whatever is right next to the Shift key is then able to comment out all the lines of code. So going back to our previous example, we have could just uncomment it, which was intentional. So we could do print my string. Let's do 2 to 5. What would happen here? So let's just clear both sides first. So typing clear and then running the code appropriately. Apologies, just rerunning the code. There we go. So we've got T, H and O. Of course, if we did a 2 to 5 to 2, that means that we skip the one afterwards and take every 2 steps. Of course, we only get T and O because H doesn't count. So I'll show that a bit closer. If we went right to the idea, let's try 1 and 4. Get a similar answer, Y and H. Of course, if we remove the step function, we get YTH. That's selecting 1, 2 and 3. Notice, of course, that one thing that I was about to make an error on, and I'd like to show you just for my clarification and for my practice. If we pick a number that is outside of the index range, so of course we go 0, 1, 2, 3, 4 and 5, there isn't an index for 6, and it will tell us that we are indexing out of the range of the available string. Just one thing to bear in mind: if you're wondering why your code isn't working, maybe consider realizing that you're using a 0 offset index and not a 1 offset index, just a common mistake. Now, we have just been completing the idea of strings, and we're going to take this level up a gear when we talk about data structures, which combines a lot of the theory that we've covered so far and puts it all together in a neat little package. And that will then be followed by lists and also the idea of function and a bit of object-oriented programming. So in the meantime, we will see you very soon. So far we've seen a few tutorials on the different data types, we've done iteration and we've done selection as well. However, when we're using Python, we might be wanting to store data, and that's a bit more complicated than simply declaring a variable and adding a value to it. When we use variables just for storing single values, that's often what we consider an inefficient process. If we look at the grocery list that we've got on the far right, that's very inefficient to just list the items in the grocery list as individual variables. For example, if I've already crossed off the milk because I've bought it, how do I get rid of item 2? The item 2 is persistent throughout the program. We can't delete it unless we make it equal to 0, or as we know, it's nullifying it. That's what it's known as. Or if we give some other value to it, which means that it's off the list. That's not very easily done with variables, but Python does accommodate the need for eliminating items in the list by actually having specific data structures for that purpose. So data structures do exist in Python that help us store a collection of different items. And when we refer to a collection of items in Python, in this case for lists, we are referring to organized collections. So as I mentioned, we've already got lists as part of our arsenal, And we can also have other things, for example, tuples, which is used sparingly, sets, which we don't really use at all, it's just more of a mathematical construct, and dictionaries, which we use, well, extensively actually. Sets aren't really that special, they only have a few case uses, especially in mathematics, but you might see them in the wild in Python. Lists are essentially items that are ordered and they have a specific index with them, just like we saw with strings earlier. If we look at the following collection of items for a grocery list, we can see a list with different items in it. They're all strings and we separated them by commas and we've given them the value to the variable name groceries. So if we look at the following example over here that I created earlier, you can see the example of a list over here, and this is the essential idea of having a list with square brackets as items which are strings and they're separated by commas. Now, one thing that I was alluding to in the previous recording of this section before I had to discard it is the idea of different types of strings. When I mean different types of strings, I'm referring to the double quote, single quote, and triple quote nature. In a double quote, we can't actually split the string over two lines, and if I press enter over here and try and break it, we get several errors over here, as you can tell by our quite humorous extension. The same exists, of course, for a single quote as well. If double quotes and single quotes are identical. And of course there's even more errors, so I will just have to restore this situation so we can get back to 0 errors. Triple quotes are actually an extension of single and double quotes because they can go over multiple lines. There are case uses of using double and single quotes together, especially if you're having a quote inside of a quote. So for example, if I'm going to say a quote over here, so the quick brown fox happily jumped over the lazy dog. Still it's still a string, but we've got one string inside of another string. Rather, we've got one quote inside of another. If I, of course, change that to double quotes on both sides, what happens is that this second quote ends this first string, and then this second double quote starts off another string, and we've got a word in the middle that doesn't exist in a string at all. So that's where you would use single and double quotes together, and that's all I'm going to say on that matter for now. If we look at another alternative example, we can also be able to index index lists as appropriate. So if we look at the following example over here, we've got groceries, and we're going to print something over here that item number 3 on the list is groceries 3. Of course, this is intentional as to try and point out to you that item number 3 on the list is not the third index, because indexes start from 0. So some of you might have noticed that, and well done if you did. So in fact, to get bananas, we would have to do index number 2. We do that here. So of course, we're going to just delete all of our string stuff, and we're going to try and write that statement out here. Print item number 3 on the list is, and we're going to add the index for the groceries 3. This is otherwise known as concatenation. So whatever this produces, which we hope it produces bananas, is added to the end of the string. This only happens, of course, if both the items are strings of string type in the first place. So now that I've saved it and just checking that everything works, I'm going to try and print it. Item on the number 3 on the list is cereal. Of course, I should have remembered that I'm looking for item number 2, bananas, and changing that accordingly as well on my index over here. There we go. That was the intention. Exactly as I was expecting. Lists don't just have to have strings, and essentially you can have many different types of data types inside a list. So we've got a collection of different types in here, so if we just show that here, so my list is equal to 34 true, I'm going to do another word here, blockchain maybe not, so Bitcoin might be a good one, and 3.14 or the 1.618, which I assume to be the golden ratio. this still does work. It's still a list of different items, but they're all different data types. So my list of 2. So in fact, I'd rather like to print that as well, just to make sure it shows up on the screen. I'll show you what happens if we don't print it on the screen. So by pressing play again, or by just actually reloading the previous command, we get Bitcoin. If I don't put the print, we don't actually print my list 2, we're just merely stating that as an index. We have to actually put print around my list 2 to actually get it onto the screen via the terminal. So that's essentially the idea of lists, and we can actually use lists a bit more powerfully. We liked the idea of iteration and selection, which was forming the idea of loops. So we can actually loop through lists in order to get every item on a list. That's exactly what iteration was designed for, to be able to get every single item as we work through a specific construct using a loop. So we have our groceries list from earlier, and we might like to loop through this whole list. What we do is we use a for loop, as we discussed earlier. So for item in groceries, we're going to print each item. If I get my laser pointer out just to show you. So for each item in the list that we've called groceries, print the item. It's as simple as that. What we would expect, of course, is to get each item printed out separately, one at a time, on each new line. Also, if I just try that here earlier, what I'm going to do is I'm going to comment out the code, and on a Mac I can do that with the command and I believe the /, which is right next to the right hand side shift key underneath the question mark. So I can do that for item in groceries, print item. Of course, if I'm just clearing this section over here and running it as appropriate, there we go. Notice, remember that we were using a counter variable. It doesn't just have to be item, it can be for good in groceries, print good. We just have to remember that these two variables are identical. Same thing. This is just a generic variable that we've named for ourselves for our own convenience. So for good in groceries, print good. One thing as well in loops is to always remember to have your colon here at the very end to make sure that you're able to indent the code block over here. So we head back home to our presentation. We've just a bit more left to cover on lists. Remember, lists and arrays are not equivalent. Arrays are slightly an older construct that was more popular when doing C or C++ programming, and it's still widely used in a lot of different other languages. Python doesn't have lists. I apologize. Python does not have arrays. The difference between lists and arrays is a bit more complicated, but the bottom line is that lists allow you to have different data types, for example strings and numbers, floats all together, and they're also more flexible, which means that you can edit them. With arrays you can't do that, and that's why we don't have arrays in Python. Now, the lists that we've spoken about so far are what we'd consider one-dimensional lists, because we can go from left to right in, well, one dimension. That's what we do when we draw a graph. We draw two-dimensional graphs on paper because we go left to right, up to down. That's what we mean by a dimension. What ways you can go. Lists have 2 dimensions. We can go left and right, up and down as well. And those are what we call lists inside of a list. They are known as 2D lists, i.e. two-dimensional. And if you think about it, we've actually seen two-dimensional lists. They're actually tables. If you think about it, we have one record over here, and we'll touch on records next week. So this is the first record, this is the second record, and this is the third record. It's probably easier to think of it as row 1, row 2, row 3. But we also have data that is going down in columns, and they're all grouped together through some relation. We think about this in the context of something that we might see more. We could have, for example, months as being the row and columns as being the year. This is just some data that I've just made up out of nowhere for something, and essentially probably an item or a good or a currency. Essentially we've got data that are grouped in 2 different dimensions, one by the month and one by the year. Showing that more appropriately, this is one dimension, well, dimension number 2 rather, that I've shown first. So this is the first of 2 dimensions, and the second of 2 dimensions going downwards. So we've got left to right and up to down. We try and do that as well in our Python. We can simply, if I just create a new file, so I'm just going to call it, as I said in the presentation, list2d.py. So we say that data is equal to, now I use square brackets and I press enter, and that automatically sorts out the indentation for me. Then I create another square bracket which creates a list inside of a list, and then I can just fill in the spaces accordingly. 15.2, 16.2, 17.3. Once I press a comma, I go onto a new line, keeps the indentation. 20.1, 23.2, 25.4. And another one, 30.3, 35.6, 39.9. Now, that is essentially the table that we constructed earlier. And some of you might notice, from some of you that are studying maths, that we've essentially got a 3x3 matrix. This is also how matrix multiplication can also be sort of constructed within Python, if you choose to go that far. Lots of different possibilities exist for lists, far beyond the usual idea of just listing different items. So that's the idea of a 2D list. How do we work with them? Of course, we can't just make them and just leave them be. We've got to do something with them. We discussed earlier the idea of nesting, and nesting also has some possibilities when we're working with 2D lists. We do this, for example. Essentially what we're doing is we're going to add up all the different prices that we've got inside this, well, matrix of information, so to speak, if we were being mathematically accurate. We start with a counter variable of 0. So right at the start we're going to have a variable that is named total, and it starts at 0. The first line over here is the first line of our for statement. So for loop rather. So we're going to loop through each list inside a list. So for row in data. So we're inside a list. We're inside the data list, and we're going to loop through the first item, which is list number 1, the second item, list number 2, and the third item, list number 3. When we have the first row selected, so we're going to hold this first row constant, and then we're going to loop through the second loop here for the second for loop for item in row. So we're going to do item 1, item 2, and then item 3. For each item that we've got, we're going to add it to the running total of, well, the variable total. So we start at 15.2, then we add 16.2, which I believe is 31.4, and then we're going to add 17.3, which is around 48.7. And once we've done that, that's the first row completed, then we're going to move to the second row, then we're going to repeat that process, adding that onto our previous running sum of 48.7 all the way through until we're done. And once the loop is done, we're going to print the value of total once we've exited the loop. We hope to get the result of around 223.2. The only reason for this is some sort of overflow that I'm not too familiar why that is the case. I haven't actually looked into it, but there is some over precision that can happen in certain instances of Python, and I believe it's to do with some sort of overflow or precision error, although that's far beyond the scope of this course, as I'm not a computer science student. So we try and program that in our code. So we're starting with the running score of total, and a running score has to exist before the loop, and it has to exist outside of the loop. I'm going to show you in a minute why. So if we did for row in data, so we've started by looping, so we're going to print row actually, just to show you what that would be. So if we clear that, so it prints us the individual rows. It prints us the first row, the second row, and the third row, because there's 3 different items inside the list. It's all very good. But then I want to print inside each element of the row. So for item in row, print item. So now going through each row, we're going to extract each individual element as we expected. So now we've got one step closer. All we have to do now is we have to add each item as we've obtained it into the variable total. Item, and once I break out the indentation, I'm going to print the value of total. And just to be clear, this statement is outside of the loop because it's not in the same indentation level as the second for loop. If we run that, we've got the answer that we requested. Now, some of you might make the classic mistake of indenting your total loop in the wrong area. I could have used actually a shortcut for this process, but I decided to copy and paste to get the indentation right first time. If I do this, for example, where I put the total in here, have a pause and think why that might happen. Remember, you're looping through each row in the data, and each loop will reset the running sum of total. We're only going to get 105.8, which is actually the value of when we add these three numbers together. The reason is that once we've added the first three numbers together, what happens is the loop goes back again, and it resets the running score of total, so that then we add all these numbers in the next row. Then we add the total sum of the next row, which looks to be around 68.7 or something, I assume. And then once we've assigned that to 68.7, we're going to be resetting that because we're going through another loop inside here. And then that will be cleared back to 0, and then we're going to add these three numbers again. So in essence, if we put the total sum inside of the first loop, we're just going to be resetting it every time we obtain a new row. By putting it outside, we ensure that the total sum is not affected by the state of the loop over here in between lines 8 to 10. So it always stays on the running sum, and the sum is never reset, it's only accumulated, as we expect with 223. So that's essentially the idea of 2D lists. They do have some applications. As I said, we can store data in matrices. One of my first lessons in 2D lists was the example of the game 2048, which many of you might have played years ago. That's also an example of a for loop with a running sum to make sure that you've been able to get to 2048 by adding each of the squares appropriately, and you lose when you can't fit any more squares or merge them together, and the score that you get in the total is a score by going through all of the different elements of the 2D list and adding them together. So that's one application of a 2D list. Next, we're going to briefly talk about tuples and dictionaries before we get onto the main subject of subroutines. Tuples are one of the other data structures that I'm going to briefly touch on. Essentially, tuples are basically immutable. They can't be changed after they're created. Now, if we look at this example over here, we've got a tuple, which is basically a list surrounded by rounded brackets. And if we try to print the first element of the tuple of weekdays, we get Monday. The reason why we might use tuples is because since they can't be changed, we can use them for stuff that's always constant. For example, days of the week, as if that's ever going to change. Now, I didn't actually mention the idea of lists being mutable because I felt that this wouldn't be part of the process so far until we get to adding and removing items from the list. But I feel it would be quite nice to actually mention it now. So, if we go back to the groceries list over here, and I'm just going to comment out the list, it is possible to actually reassign a value on one of the items in the list. So for example, groceries 0. The index of groceries 0 is apples. Say I didn't want to buy apples, say I wanted to buy pears. What might happen? Well, using this sort of idea, if I print groceries and then press play, I've now changed the first element in the list from apples to pears. If you want to be more precise and confirm that, try adding the index as well, and I get pears. This is what I mean by lists being mutable. This can change depending on the values that you want by changing the index in which a value exists. Later on, you'll be also able to see that lists can also be mutable by adding or removing items specifically. However, if I go back over, tuples are what we call immutable, so they can't be changed. And this is quite convenient, for example, if the names of the weekdays don't really change. I mean, they're not going to change anytime soon. They do work just like lists, but they're not changeable. I try, for example, well, let's give it a shot actually. List.tuple.py. And try weekdays again. Let's give that one an idea. Or let's do months of the year. Months equals Jan, Feb, March, April. Because tuples aren't mutable, I can't do something like this. Enero is the Spanish word for January, so I can't do, try that, see what happens. What's going to happen is that we're going to get an error. So tuple, which is what we've got here, an object which we'll come back onto later on, if you'll excuse me for a second, does not support item assignment. We can't basically change an item in our tuple. Even if I tried, it's not going to be able to change. So no matter what I do, it's always going to stay as January. And if I look at the whole tuple as well, or tuple, some people say, it's always going to stay like that. It's quite useful, for example, when you have a constant list, essentially, when you have a list of items that shouldn't change. To edit lists, we're going to have to use methods, and that will come after we have a discussion on dictionaries. We've discussed the idea of lists, 2D lists, the difference between a list and a tuple, and now the only data structure that we have left is the idea of a dictionary. Dictionary, just like a English dictionary would, allows us to create an association between, well, in an English dictionary, a word and a definition. But in a dictionary in Python, it allows us to have an association between a key and a value, i.e. we can associate a value to a specific key in question. And each unit of information consisting of a key and a value is known as an item. Look at the following example from dictionaries.py. We can see we've got different types of coins available to us. So we've got Bitcoin, and we've given it the ticker BTC. And we've also got Ethereum, which is given sort of the ticker ETH. And essentially we've associated BTC to Bitcoin and ETH to Ethereum. So when we index a dictionary, we do it slightly differently. We don't just provide the number in the order of the in the order in which the items appear in the dictionary. We actually provide the exact key that we give into the dictionary itself. And if we process this following line accordingly, we get the idea of Bitcoin. Dictionaries in Python behave the exact same way like a language dictionary. Well, in the English dictionary, you would look at the word, essentially a keyword, and then you'd look it up and you'd get a definition in hand. Dictionaries in Python work a bit similarly, but have a bit of a nuanced difference. We look at the idea of the item. We've got crypto, which is the key, in this case BTC or ETH, and we've got the associated definition, i.e. the value, which is a digital currency, for example Bitcoin or Ethereum. When we add both of the two units together, we get an item. If we look at the following code here in the IDE, we're going to do dictionaries.py, and I'm sure most of you have got familiar to that point. I'm going to do something slightly differently. I'm going to think about, let's take an example. Let's think about countries. Do strings, for example. GB would be Great Britain. FR would be, for example, France. And ES would be Spain. Now here I've produced an association between the two-letter acronym and the country in question, which is normally what you see on the back of registration plates in the European Union, to my knowledge, of course. If we want to get, for example, the definition for France, we'd have to first enter the keyword associated with it, or the key itself. So you print countries, which is the dictionary, and FR. So if we run that code there, we get the idea of France. Or we either get the value of France, but you get the idea of what we would be expecting. Clear that as well. Do another example just to show you. We can have ES, which if we play it gives us Spain. It is possible also as well to be able to reassign the value of a key. So for example, let's say that ES wasn't Spain, let's say it was something else. So countries, we get the index, which in this case is the key. Let's say it's Estonia. Alright, any Estonians watching? I do like Estonian people quite a lot. So if we run that, we've now changed the dictionary to Estonia. If I print countries and comment this line out, I think it's quite evident to see where that comes from. You see, we've changed the value of ES to Estonia, and that's followed through. So that's the idea of a dictionary. You will use it in some cases. It's much more useful than you think, than, for example, using tuples or sets, and it does have its uses, but it's important to understand the idea of a key and a value and how they all come together to form an item. Dictionaries are essentially just lists with keys and values rather than just a single value itself, single item, which can be of any type of data. And essentially we have an association between a key and a value, so it's what I call a by data sort of relationship. Not that it is the official term, but it just helps me to think of it like that. I'm relating two different bits of information together and then listing them out accordingly. The next section we're going to discuss the idea of subroutines and the idea of functions and methods, which will help us to understand objects later on. So far we've seen various different data structures, and we've also seen the idea of looping through iteration and selection. Next we're going to talk about something that's a bit more fundamental to the idea of programming, and we mentioned it very much at the start of the course when we were talking about getting a computer to repeatedly do something infinitely many times, more than a human can. That's the idea of something that we call subroutines. Well, subroutines we've already discussed about blocks of code. Subroutines are essentially blocks of code that are what we call self-contained. That means that they run independent of other code and they can be moved around, which means that they don't run from top to bottom. They're essentially isolated and they can be only run when we use them. Many programs, for example, if we've got, for instance, a drawing program where we need to be able to move a cursor from left to right, we need to have, for example, a function that shows the cursor on the screen over and over again. There are many programs where the same task may need to be repeated multiple times. For example, if we're connecting to the internet, we will need to make sure that an internet connection is sent out every second from our computer to make sure that we're getting the right amount of data in. If we repeat the code many times, it obviously looks inefficient over and over again. What we can do instead is we can write the repeated code as a subroutine and then call on it when we need it, and you'll see that a bit more later on. The fact that we can only need to define the code once and then use it as many times as we need is a very big advantage. When I refer to the idea of calling a subroutine, it's when essentially I'm running that block of code inside the program. And in Python, there are two types of subroutines that you should be made aware of. The first one is the idea of user-defined functions. It's functions that we specifically create for the program to be able to use. The others are essentially methods, and they're more designed for the data structures that we've seen so far, and they're basically designed right from the get-go in Python, right out of the box. First, I'm going to cover functions, as I believe it's a bit more fundamental to the idea of subroutines, and then we'll move on to the methods afterwards. As you might have noticed over the past few slides, that much of Python and computer science has a lot linking to each other in terms of its link to maths. So Python is linked to maths, computer science is linked to maths, and therefore Python and computer science share a lot of dissimilar features. In maths, you might have studied the idea of functions, and functions are basically sort of ideas where you can take input values and get one output value in return. Here's one example of a function. So we've got the number 3, which we push through a function f of x. So 3 would take the place of x, so it would be f of 3, which equals 9. Here we've used the input as 3, so the argument of the function is 3, which is the input, and hence quite logically the output of the function, or the return value, what it spits out, what it returns to you, is the value 9. The function that we were describing above would be the idea of the x squared function. So the input is obviously x, which is the argument, and the output is x squared, which is what it returns if we supply a number x. Our input, as I mentioned, is the argument of the function, and our output would therefore be the return value of the function. Python takes this idea a bit further. We don't just have to use mathematical functions, we can also use our own functions as a user-defined function, i.e. we can define them ourselves, and don't just have to take integers as inputs. We can actually use all types of different data types, and they're not restricted to just integers. There are some functions that don't actually return values, and those are what we call procedures. Here's an example of a procedure that I wrote earlier. We defined a function called greeting, which we've given the parameter name over here, and notice that the name variable over here isn't an argument because we haven't actually called the function. Here we're simply defining the function over here, and when we define a function and we pass in some variables to in the brackets, those are what we call parameters. They're not arguments. They would only be arguments if we're actually calling them, the function themselves. Here what we've done is we've defined a function called greeting, and we've said that it's going to take a parameter called name, and then we've actually declared a print statement with the string hello, a space attached, and then a name. So whatever name we pass into the function greeting will end up being added to the end of the string, preceded by the word hello. If we pass the name Satoshi into the function greeting, essentially the scheme would look like this. The input is Satoshi, the function works with greeting Satoshi, and then we get the output hello Satoshi, which is what we get over here. So whatever we pass into a function will therefore be printed with the word hello in front of it. There might be some instances, however, where we might want to store the result of a function. Here the result of the function was simply to display a message onto the screen. But sometimes we might actually do some mathematical operations, and we might want to store that data like within a variable. This is where the return keyword becomes much more paramount. Now, so far we've discussed the idea of functions, and we've also discussed the idea of some built-in functions that Python provides for us. For example, the print function. Now, those sorts of functions typically work on most different types of data types that you'll uncover in Python. There are some sort of subroutines that don't work on any type of data type. There are some subroutines that only work on specific types of data types. And these specific entities that we're discussing here is what we call objects. Now, there are different types of objects that you've definitely covered throughout the course of this session so far. That include strings, integers, and lists. Now, methods are unique in the sense that they only operate on the object that they've been designed to work with. So if we compare that to functions, for example, print, they work with all data types. They work with strings, they work with integers, and of course they work with lists by comparison. Now, Python has several different types of methods that is available to you. So, for example, upper and lower, as you can see here on the far left, only work on strings. Append and sort work best with lists, and values and items only work with dictionaries. Notice, however, that not all methods tend to work in the same way. Some will require more arguments than others. If we look at examples of methods, we can have a look at this one by from stringmethods.py. Now if we look at line number 1 over here, and I'm just going to get my laser pointer, you can see that MyString is given the string blockchain, i.e. we've created a variable, called it MyString, and we've given it the value of a string that spells out blockchain. In line number 2, what we've done first is that we've made MyString use uppercase by using the upper method. Then we've assigned that value to newString. So when we print newString, we're going to get blockchain in big capital letters. Now methods are essentially, well, we use them a bit differently, because what we do is that we use the object's name, the variable name that we assign it, and then we use a full stop and provide the method name. Even if we don't provide any arguments, we still have to actually use the brackets, as it is still a subroutine at heart, and all subroutines require us to declare how many parameters we use or how many arguments we supply, and even if we supply 0 arguments, we're still going to have to keep those brackets just empty. Now, if we called MyString.upper without the brackets, then what essentially happens is that we return the subroutine itself, the function, but we don't actually execute it. Now, on the following slide over here, I've sort of shown the same thing here with a different sort of string. So if we take London over here, and then we do lines 2 and 3, as we saw in the example, then what happens is we get London in big capital letters. What I'm going to do is I'm going to clear the terminal here. If I could also go the opposite way, let's say Milan, which is a city in Italy. What I can do is I can also use other methods that do the opposite effect. For example, lower, which is shorthand for lowercase. There we go, and I've changed the case of the word to be lowercase. Now if we head on back to the presentation. Methods do have their uses when you work with lists. Let's have a look at the following list over here. In listmethods.py we've got 4 different names. And there are some methods, which we'll touch on momentarily, there are some methods that actually don't require us to assign a new value to the variable. We don't need to assign a new variable to the value of the sort method. So we don't need to do, for example, new names equals name.sort. What happens is that the method works appropriately on the list and then replaces it in its place. We don't need to change the variable name. And then by simply printing it, we've been able to order the list appropriately. This is, well, of course, what we call in-place methods. So we edit the original variable here on the top, and then we replace it with what the result would be, as we didn't provide any arguments. There are functions, such as sorted names, which do an identical job actually, but what they do is they create a new copy of the object. So we have 2 different versions of names floating about. The original names variable is left untouched, but we actually create a new object, which is here a new list. It's all sorted, but we need to actually store it somewhere under a variable name. Now, one thing that I'm going to emphasize here is be careful when you are using a method or a function, because the two of them work very differently. So if you don't know how to use them, check and check and check again. There are also other examples, for example, the methods for dictionaries. So we've got a dictionary over here. It's my dictionary, and it's got two different items, a key and a value, and a key and a value. So what would happen if I printed the values? Well, let me try and have a look over here. So we've got dictionary methods.py. So I'm going to be a bit short. My dict equals, well, let's take the example from the code, BTU, which I believe is the Bitcoin ticker, and we've got, let's try Doge rather, which is Dogecoin. If I simply print, and I have to remember, I have to use the print function here because I'm trying to display it on the screen. If I, my dict.values, remember there's no values that I need to attach, so I can just keep that. And there we go. We've got an object containing dict values of the Bitcoin and the Dogecoin, which is exactly what we were expecting. We were expecting the values to just simply be printed out. And if you want to go one step further for your interest, you can also convert this result to a list, because it's a list of two different items, which hopefully should work. Fantastic. And even more, what I can do is since it's a list, I can index the first item. Fantastic. Now, just to be clear here, if I just did my dict.values without the parentheses, let's see what Python would say. For that, let's just clear the console. It doesn't actually print anything, because essentially we haven't executed anything. We've loaded the method into the program, but it actually hasn't been executed. We even try this, for example, my dict.values. Again, we need to print something to the terminal, and that's only achievable by using the print function that I discussed earlier. As you can see there. Now heading back onto that presentation, so that's an example of using values, and essentially methods help us to extract specific information from a specific type of object. Sometimes these objects can be quite rare and bespoke, and they require special methods that have been designed for them. However, notice that this only applies on the object that we're calling the method on. Sort of makes sense if you think about it. If I did my dict2 equals, well, let's do something completely different. iPhone is equal to Apple, and Pixel is equal to Google. Notice that even though I've got two different dictionaries that vary by just one letter, we still have to separate the two values in order to print separate results. So if we print the same program again, what can happen is that essentially, because we've printed the values of my dictionary, and then next I've printed the values of my dictionary too, we get these values out separately, and that shows that even though we have the same, we're working in the same program, two different objects can give two different results. There you go. And also you can use loop method results, for example, when you're using a condition to specify a specific selection that you might want. Now, functions always have a name attached. I think that's been quite clear so far. There are some functions, however, that don't require a name. These are what we call lambdas. And lambdas essentially comes from a branch of mathematics called anonymous functions. So if we look at this example here, we've got a square, and we've provided a lambda x, and we've mapped x to be equal to the value of x squared. This is obviously, I've said, in a bit more of an advanced mathematical thinking. Essentially, this function here, that we've given it to the variable square, essentially is a function that if you pass in the value of x, you simply square it, and it returns it. So if we do square 3, it's not surprising that we get 9. Now, the one advantage of using lambdas is that we don't actually have to name the function, and although it's still exactly the same in terms of operation with other functions, they just haven't got a name, which is why we call them anonymous. If I head on over to my the S code, we can see that square is equal to lambda x, which is x to the power of squared. For example, I could also change this to cubed. So lambda x will be equal to x cubed. So if we provide cubed 3, see what happens when we try and run it. Well, again, we need a print function. To be precise, I've been omitting the print function in the main presentation because often I'm a bit more naive and I'm thinking that I'm using Jupyter Notebook. However, if you want to print something to the screen, you do it the old school way, which is by using a print function. And that's what happens, you get the result of 27. Now, you do specify a parameter, and you also specify the value that you need to return. So we return it implicitly because lambdas always return things. They will never not return anything unless there is the ability for it to be that explicit. So the value of x to the power of 2 is implicitly returned because we don't need a return keyword this time. And again, you can store the lambdas as a variable. Now you can see here that we've done square and put 3 in, so square is a variable, and we've plugged in a number 3, and the anonymous function attached to square gives us the result of 9. Next week, when you're studying pandas, Imran will also be talking about certain sorts of lambdas that you might use to sort your data. It's going to be a very exciting time. We've touched on the idea of objects briefly in the previous slides. We're going to sort of rationalize it and add a bit more flesh to what we were talking about. Now, we've certainly seen different types of data, but we sometimes have to require something that's more bespoke for our specific needs. Data types are essentially treated as objects in computer science, especially in programming as well, but more importantly in computer science. Especially in the scope of programming, and certainly in the scope of Python, all objects that we encounter can have specific attributes, which are essentially just specific properties of the object, and specific methods attached. And of course, we've spoken about methods at length during the previous sections. Sometimes, however, we might need to define our own types of objects. For example, we might be modeling something, for example, a human being, a pet, a car, anything you might think of. Anything that requires a computing perspective in terms of rationalizing the sort of blueprint of a car, a dog, or a human being, and allowing the computer to sort of mimic its behavior. Creating our own objects is otherwise known as object-oriented programming, otherwise given the acronym OOP, because we are creating objects that we want, that behave to what we are conforming it to be, and it's oriented around, well, the objects that we've created. It's quite straightforward in that respect. Now, to first create objects, we first need to define the object blueprint. This is essentially the sort of high-level overview of what an object should behave like and how it should be created. And once we've defined the object blueprint, we are able to create objects. This is otherwise known as the class. Now, defining classes in Python requires a very specific procedure that you have to go through, and you can't just define classes at will, because you have to make sure you fulfill certain requirements. So, in Python, how would we define such a class? Well, in Python it's relatively more simpler than other languages, but it still requires its fair bit of ideality. We essentially use the class keyword, especially in the opening stages, and then we supply this sort of function that we are required to have from Python, and it's basically 2 underscores init and then 2 underscores followed by 2 brackets. It's a function at the end of the day, but this init is short for initialization. So in this introduction here, we have defined a class called human, and this whole block of code is a blueprint for how a human is created. So when I said init, I was referring to the idea of initialization in the context of classes. So we have a keyword called self, we have name and age. I'm going to come back to self momentarily, but for now we're going to we're going to create an object, and we're going to use the name attribute to give the object's name the value of name. And same with age. Age was an argument to the function, so the object's age is then given the age. It's quite similar to a human being. When a human is born, it's given a certain name, so the human's name, it's, well, self, and the human's age is given an age. Probably not so much when it's born, but, you know, it's a high-level overview. So when we have an instance of the human class, we use the class name, human, and then we supply the two arguments that we need. We don't supply the self argument because it is implicit, as you'll see momentarily. Now, this is important to understand. We have two different types of human objects. We have a human one, and we have a male, who is David and is 23 years of age. We've also got a second type of human who is completely different to David, and she's called Sarah. She's 33 years old. When we do print of human one name, we get David, but because it's David's name. But he's the age of 23, so we're not going to expect to get 23 for when we print human 2's age, who is Sarah, because she's 33. And that's what gives rise to the idea of self. What does self mean? Well, it's quite hard to explain what self means to a very simple programmer, but the formal definition is that self is a keyword, as a reference rather, to the instance that we are referring to the object rather that we're referring to. Are we referring to human 1 or are we referring to human 2? Well, if we look at this example again, human 1.name, we are trying to obtain the name of human 1. We're not trying to obtain the name of human 2. We are trying to obtain the name of human 1. Well, in this case, himself. When we print human2.age, we're trying to extract the age of human 2, herself. So tabulate that and some more information here. So human 1, his name is David and the age is 23. Human 2 is Sarah, who is the age of 33. There are two different instances of human beings because we've created two human beings out of the same blueprint, and they have different names and different ages. So when I run self.name in the self.name equals name, that's basically what we call a constructor of the class, and it says in layman's terms that you have to assign the variable itself a name attribute, or a property that's equal to the name that we've passed in the argument in the constructor earlier. The self keyword is much more useful actually for when we use class methods. We don't just use it for init functions, we actually use it more for when we write our own methods that are designed to classes. I'm briefly going to diverge from there and show you how it's done in real practice. I'm going to use a human this time. In fact, I'm not going to use an animal this time. I'm going to actually use something called a car, which was one of the first tutorials I learned in object-oriented programming. So, we look back at our code over here. We've got the idea of using class, so we're going to do car. So this is going to deliver us any car, and just to make sure, I'm going to be using Python, so not writing a text file. So no errors there so far. There we go. So define and an underscore init, and we're going to do self, and we're going to do self and age. Maybe a car has a certain lifespan that it exists in. So self.age equals age. That means that when we create a car from this car blueprint and we initialize it, i.e. we give birth to a car, we make sure that the car's age itself is equal to the age that we provide in the argument of the creation of the object. So for example, car1 equals car, and we're going to give it an age of 13. So I'm going to just save that as class introduction cars.py. Could have done camel case, but I decided to save the time. And we're going to do car number 2, and on the Mac I use the Alt, Shift and Down key to sort of duplicate everything. We need to do car 35. Might be an old car. What I'm going to do, also got to change it to car 2, else we're overwriting car 1. Print car1.age. Now, it's not a method. In this case, we don't need to supply brackets because it's not actually performing a function. All it's doing is it's just obtaining a value for the property of a car, again known as an attribute. Print car2.age. Well, if we have a look at what happens here, let's clear the screen, let's press play. We get two different ages. We're getting the exact same type of information, or the same nature of information would be a better word, but we're getting two different results. And that's what it means by self, because the car's age itself here, when it's assigned to car 1, is 13, but here on line 6 it will be 35. And that's what we mean by customizing the output of the function specific to the object that we're using. Can we define methods? Well, we've clearly discussed about methods earlier, and we certainly can for classes as well. What we have to do is remember to always keep the self keyword, because we're relating the method to the instance of the object itself, not the blueprint. If we look at this example here, we've got, on a special line, we've got define greeting self. Now, what it means there is that the object itself is going to have a greeting ability. So it's going to be able to print to say, hello, my name is self.name. And obviously, human one was called David. So when we do human1.greeting, remember, because we're not actually providing any arguments after the self keyword, so essentially we're going to get, hello, my name is David. Now remember, you always need the self keyword to come first because it's implied here when you create an object and use its method. So really this should say human1.greeting self, but because it is so obvious from the context of some very hardcore OOP programmers, it's sort of hidden away and you can't see it, but it is implied when the program is run. You must include the self keyword in any method declaration because it's implicitly passed on by the computer. It basically takes care of you. Now, some attributes such as name do not require brackets because they're not subroutines. Again, I mentioned that earlier. If you want to access a property of an object, you don't need brackets because they're unilaterally, well, that's not the best word. It is very much synonymous with the idea of the object. The random brackets are synonymous with subroutines, and we don't need them here because they're not subroutines anyway. Before I head off, I'm just going to show an example here. So let's do define toot self. All we're going to do is say print beep beep. So beep would be my appropriate. So print, or rather we do car1.beep, car2. Let's just keep car1 for now. Number 2 have our brackets. Classic rookie mistake. Oh, look, beep beep. Now, if we run this code again, and there is just the mention of 13 and 35, which are the ages of the car. Might just want to clear that here to get more space. Now, car1 dot beep, and we've got car2 dot beep. So we're going to get two different versions here. In fact, that wasn't the appropriate. For those of you that spotted, well done. That was not the appropriate line to comment because it was necessary for us to actually create our variables. So we're going to get there you go, two versions of beep beep. Notice that there isn't any age printing because I've commented it out. Thankfully, this is the end of the Python course. There are a few important details that I'd like to give you before you go away. The self keyword is always given by the computer. It's implied. You won't see it, but the computer is giving it. So give it always first on the computer. So whenever you do method declaration or class creation, remember that self is the most important word in the book. When we create the object, it's otherwise known as construction, and we use the init method to do this. So I like to think of it more as when you make an object right at the very end, or when you give birth to an object, more like how humans give birth. Now, objects don't just apply to, for example, modeling humans or modeling certain things. They can apply to anywhere. You can generate the model of a user, and it has some uses, for example, in data science, especially when you're covering pandas next week. To me, classes are essentially blueprints, and that's actually how the name of class came about, because it was done first by a biologist. So they're basically just blueprints for just like the blueprints for DNA, we use blueprints in programming to make sure that everything is intact and we have everything that we would want from an object. When we create more than one object from a class, that's otherwise known as instance of a class. So we had human 1 and human 2, we had David and we had Sarah, I believe, and they were both instances of the same human class, provided that we actually created one. Although we did actually. And specific objects, specific properties of an object, they're otherwise known as attributes. Now, they don't actually run any code because they're not subroutines, but they have some specific uses, for example, the name, the age, or gender or of a human being, especially if you're modeling human beings inside the program. Now, thankfully, that is the end of a very long and arduous session on Python. I hope you understood it very well, and I hope you make the best use out of your Jupyter Notebook. Now, all the best for the future lectures, and I hope to see you soon. And if you see me on the campus, please feel free to say hi, and I hope you enjoyed the Amazon gift code vouchers. Thank you very much, and all the best.